Okay, here we're going to look at how do we treat experimental data. We're going to assume that we do an experiment multiple times and we collect data. For an example, we might measure, which is what you're going to do, measure the period of a pendulum several times. You will not get the exact same value for the time during each trial. And the question we have to figure out is, why does this happen and how are we going to handle it? We will assume that there really is, if you will, a true value for the period of the pendulum, and our measurements are imperfect ways to use tools to try to get at what that real value is. The question is, how do we use our data, our multiple trials, to estimate not only what is the best value for the true period of the pendulum, but also how close we got to it. Now, one point is the file I'm going to be using here was created by a program called Mathematica. The file will be posted on the website in what is called a CDF format. The file is interactive. You can actually use this file if you go to the Mathematica website, which will be linked on the class website, and download the CDF player, which is free. Then you can open up this file and use it on your own. And that includes the fact that several of the tools on here, which you will see, are interactive. I would highly suggest doing that, and you can then follow along some of the calculations. Now, as to why we don't always get the same result every time, we can cite three basic reasons. Now, this aspect of doing experiments is called experimental error. However, the word error here is unfortunate, but it is the term that is typically used. It doesn't mean mistakes. It really means some degree of uncertainty. And this unfortunately does lead to the misunderstanding of the first reason why you might have different results, namely, you made a mistake. It's the infamous human error. That's not what we mean. That may happen. You may have made a mistake, but that's avoidable. If you do make a mistake, answer to that is quite simple. Fix it. That is not what you're citing when you're talking about sources of experimental uncertainty or experimental error. What they really mean are the second two things here. First is that there could be what are called systematic errors. That typically comes from your instrument being, for an example, miscalibrated, so that a stopwatch is running too fast, or you put a mass on a scale and it consistently gives you 10 grams too big. That can often be fixed by running some sort of a calibration routine on your instruments. And in effect, they should always be calibrated carefully before being used. For our purposes, we will assume our instruments are sufficiently well calibrated because we're not going to be making incredibly precise measurements. If you were doing real research, this is often what you spend a lot of time doing, is calibrating and aligning your instruments properly. The key thing about systematic errors is that you cannot eliminate them by simply making more measurements, because all of the measurements will always be too big. You can't get a measurement that's too small and have it average out with one that's too big, because the effect is always the same. So systematic errors cannot be gotten rid by simply making more trials. Random errors, on the other hand, can be. A random error means that sometimes when you make a measurement, you'll get a value that is too big. Sometimes you'll get one that is too small. We will assume that the result is your measurements will follow a bell curve. So you'll have some that are too big, some that are too small, and we'll have equally likely for it to be too big and too small. And the probability of it being way too big will be small, and the probability of it being way too small will also be small. And it'll follow some sort of a bell curve. This is the kind of error that if you make multiple measurements, you can reduce its effect. Because if I make only two measurements, I may have two measurements that coincidentally both happen to be too big, and they can't average out. On the other hand, if I make 1,000 measurements, chances are 500 of them, more or less, will be too big, and 500 will be too small, and the effects will average out, and I'll get a much better estimate as to the mean value. Random errors, for an example, could be, if you're using a stopwatch, your reaction time, because your reaction time is not always going to be exactly the same. Now, although you are a human being, you might say, well, isn't that a human error? And the answer is no, because it's not an avoidable mistake. It is a limitation on the instrument, because we chose to use a stopwatch. We could have used, for an example, a photogate or high-speed camera to measure the period of a pendulum. They're more expensive, they're a little more difficult to use, but we could eliminate some of the random errors by simply using a different instrument. Now note, if you used a high-speed camera, you could still make mistakes while using it. So we can't eliminate the human error aspect except by you being careful, but we can minimize the random error by using a more expensive instrument. Here we're talking about the fact that we're using a stopwatch. Hitting the start and stop button of a stopwatch, you can't be consistent. If you could, let's say you always hit the button a tenth of a second too late, but it was always exactly and precisely a tenth of a second. That means you'd start a tenth of a second too slow, and you'd end a tenth of a second too slow, but your value would be exactly correct, because we're looking at the time difference between those two events. However, if you hit the start button, let's say only tenth of a second too slow, but you're 2/10 of a second too slow on stopping, then your value will be too big. And that's the problem. And that's what would be considered a random error. And we're going to assume that your variation on your reaction time will follow a Gaussian curve, or a bell curve right here. Now the question is, how are we going to handle these random errors?